Hi, everyone. My name is Kevin Brodsky. I'm a software engineer in the kernel team at ARM. And I'm going to talk about a little kernel hardening today with protection keys. But first, before talking about protection keys, let's go back to CVEs. And this is the number of kernel CVEs identified per year that involve some use after free. This is stolen with permission from Case Cook's talk at LSS North America in June. I think the curve is quite clear. He did some linear regression, but as he put it, it looks a bit more exponential. So it's, I think, quite clear that use after free is becoming one of, if not the main, attack vector. So the interesting thing with use after free is that in the absence of mitigation, basically all kernel data is vulnerable to those attacks. Now, obviously, there are mitigations, more and more mitigations. But for the more and more advanced kind of attacks, it's becoming very cumbersome. So for cross-cache attacks in particular, now we have to resort to not reusing address space with config slab virtual. And this obviously has limitation and has a cost as well. So what do attackers do with use after free? Well, if they can, they will try to corrupt critical data structures, such as page tables. And our goal here is to prevent that corruption from happening. And how we want to do this? Well, we want to make that critical data not writable for most code. And we then grant temporary write permission per thread when we actually need it. And this talk is about a framework called pkeys, which is about using protection keys for kernel hardening. So just take a step back. There's been lots of efforts to harden the kernel in the past, at least 10 years, maybe even more. And we've got some pretty good hardening in terms of control flow in general. So it's much harder to corrupt control flow. We've had much better permission enforcement. We have all kinds of CFI technologies. And so achieving arbitrary code execution is getting pretty difficult. So that's why data-only attacks are becoming the main focus, in fact. So what are data-only attacks? So in this kind of attack, there's no control flow hijack. It relies entirely, at least the start of the attack, on data getting corrupted. And you have two ways to do that. You can do it in a spatial way or in a temporal way. Spatial way is an out-of-bounds write, something like writing beyond the bounds of an array. But what is becoming nowadays the most exploitable is temporal exploits, so use after free, that class of attack. And the very important thing to note is that the target object that we're trying to corrupt is written to by unrelated code. Code that is legitimate, but should not be able to write to that other privileged data. So here I'm taking a very, very, very simplified implementation of netlink send message that does a kmalloc, and because of some use after free, it aliases with some victim object, and then we have a copy from user that just corrupts that victim object. So what do we try to corrupt with this? Well, the aim is to achieve privilege escalation of some sort, and as I mentioned before, there are some critical data structures that allow you to do this very easily. For instance, page tables, because if you corrupt page tables, you can gain access to any physical memory. And there's also struct cred. If you write 0 there, you just become root. There are obviously others. But these are the two examples we've looked at so far. Okay, so now a little bit about protection keys. So protection keys basically is a way to gain a per CPU view of memory. The way it works is that every page table entry holds a key in blue and red there. And then there's a per CPU pkey register that determines permissions for those keys. And so these permissions overlay the MMU permissions. So if the MMU says read-write, and the pkey register says read-only for that particular key, then the resulting permission is read-only. So this was first made available on x86 around almost 10 years ago now, 2016 I think, with Intel MPK. It's also available on PowerPC and now on ARM64 with permission overlay extension. And interesting things I know is that the key size varies. I think 5 bits on x86 and just 3 bits on ARM64. So, as I mentioned earlier, the goal here is to use pkeys to prevent the corruption of critical data. And we want to do that by reducing write access. So we really want to focus on the most valuable targets, so really the low-hanging fruits, like page tables, because it is not an approach that can be automated very well. We'll come back to that later. So we really want to focus on this high-value data. It's a loose isolation. It is not compartmentalization. Essentially, if an attacker is able to change the pkey register, then it will bypass completely KP keys. But the assumption is that arbitrary code execution is not achieved. And it can be seen as a lighter alternative to many hypervisor-based protection approaches. So in the KP key scheme, we have, well, basic level, we have one pkey, let's say P0, for regular data, and that pkey enables read-write access, so that's for most data in the kernel. And then we allocate some pkey, let's say PC, for critical data, and by default, we will only have read-only access. So P0 the default in blue, and the critical one in red. And then we introduce this notion of KP keys level. And essentially, at the default level in gray, we only have, actually I'm realizing the slide is wrong. At the default level in gray, we only have read-only access to PC. But in the privileged level, we have read-write access to that key. And we introduce then some API to switch from one to the other by writing to the pkey register. Also, for simplicity's sake, we have static allocation of keys in that scheme. As I mentioned, on ARM64, we only have 3 bits of keys, so 8 possible keys. And so for that scheme, really, static allocation feels very reasonable and simpler. So the first use case we looked at is page table protection. I think it's quite clear, probably to everyone here, that page table integrity is pretty critical. And if you're able to corrupt them, then it's pretty much game over. And so with KP keys, the way we implement this is, well, there's two sides. One is when creating new page tables, we change their pkey, let's say to pkey1. And then we configure a pkey register so that pkey1 cannot be writable by default, cannot be written by default. And then every time we write to page tables via a legitimate helper like setpt, then we add some guard object that will change the pkey register to enable writing. So the outcome is that unless you call setpt, setpmd, and so on, you're not able to write to page tables. So on ARM64, as I mentioned, pkeys and KP keys are implemented using the permission overlay extension. And in terms of performance, we're looking at two main overheads. One is when switching the kpkeys level, meaning writing the pkey register called POREL1 on ARM64. And here it implies a barrier, which is quite costly. And the other one is setting the pkey. So when allocating page tables, we have to change the mapping of a page table page, and that also has a cost, of course, changing the page table entry for that. Now, there might also be some extra overhead with the hardware checks to basically implement the permission overlay extension, but we expect that to be quite low. Now, that's important because we don't currently have hardware that implements PoE. Well, ARM64 hardware implementing PoE. So for benchmarking, we put together some mock implementation, and essentially it's exactly the same, except that we write to another register than POREL1, and the rest isn't changed. So we still have a barrier, we still change the page table mappings. And we chose a selection of benchmarks which are quite intensive on the page table manipulation, like kern bench, lots of forking when building the kernel, or micro benchmarks, unmap and fork, and test vmalloc. Now, before I show you the results, the initial results didn't look very good. And the reason for that is that the initial implementation switched the pkey register for every time you call set pt. That's not great if you're having something like change pt range that can change hundreds of them at a time. So fortunately, there's something called the lazy MMU mode. And so we've leveraged this by saying that if you use these lazy MMU sections, you only switch the pkey register once when you enter, meaning you go to the privilege mode when you enter, and when you leave, you restore the original one. This decreases security somewhat, but the expectation is that only privileged code is executed in such a section. So now the results. So just to understand what this all means, the baseline is 617 RC1, so this is the baseline for the latest series. It's run on Graviton 3, so quite modern, ARM64 cores, and again with this mock implementation. And obviously this is a lower bound estimate because it's not the real PoE implementation, but we expect it to be quite realistic. And in orange means statistically significant, so anything not orange, you can consider it's negligible difference. So current bench, if we look at real time, well, it's very low. There's a very low overhead. Now, if you look at system time, so time actually spent in the kernel, it's less negligible. Still quite low, even without batching the page table updates, around 4%, and a bit lower when batching. Now, the micro benchmarks, so like fork, micro benchmarks like fork, and map, and so on. Without batching, we have a very large overhead because we have lots of PT changes, but with batching, we have actually pretty small overheads. The overhead decreases in the case of test vmalloc if we have more pages. So yeah, P means number of pages, H means huge pages. Yeah, so in any case, with this batching approach in micro benchmarks, we have some overhead, but it's actually quite reasonable. Oh, any question on the page table protection before I move on? Okay. Okay, now, sorry. Now we looked at another use case, which is struct cred. So again, corrupting struct cred is a very straightforward way to escalate privilege. there's already special handling in place. So you're not supposed to change live credentials. You're supposed to use prepare creds and commit creds to change the cred pointer in the current task. But the problem is that that's not enforced. So an attacker is actually able to write to live credentials if it, again, with a use after free, for instance. So the idea is to enforce that current cred is actually not writable. So there's two cases to consider. I'll go over this briefly. So one is the prepare creds plus commit creds workflow. In that case, it's actually quite simple. We can just say, okay, prepare creds allocates a normal object that's not protected, and then commit creds moves that object to protected memory, meaning with a non-default pkey. With override creds, we can't do this because override creds doesn't essentially return a new object. It doesn't eat the reference. So we have to have a new API, protect creds, to manually move that object. All this, so these changes are required because if we directly had prepare creds allocate the object in protected memory, we would have to change a lot of code because all code manipulating credentials would have to change pkeys level. Some details, because cred is allocated with KMM cache, we have a new flag to change the pkey, meaning also that the slab helpers need some more pkeys level changes. Now, an interesting problem is that cred objects are filled with RCU, like many things. But RCU doesn't know if an object is protected or not. So right now, we just switch pkeys level all the time in RCU. So that's not optimal. Now, having said that, I have done some benchmarking. And using the same benchmarks as here, the overheads actually seem negligible in all those benchmarks. It doesn't mean that they're actually that negligible, but at least on those benchmarks, nothing obvious shows up. Also, an important limitation is that the cred pointer in the task struct remains itself writable, so the attacker can still change that pointer. That is more difficult to fix because pkeys are a page level protection mechanism. So we can only have one pkey per page, meaning that the task struct itself is much harder to protect because if we wanted to have the whole task struct protected, we would have to change every single piece of code that tries to write to it. And this is, in fact, why this pkeys mechanism cannot really be automated to protect everything, is because essentially we have to control what writes to the struct. Now, there's some ideas on maybe we could split out a part of task struct that contains critical data, but that's much less straightforward for sure. So, just the state of things. I've posted the latest version of both series last week, a week before. So there's one series that implements the pkeys framework with the ARM64 implementation, and then the page table protection, which is mostly generic. And then another series for cred hardening, which is entirely generic, nothing ARM64 specific. Something I should have mentioned earlier is that pkeys is by design generic. It's not specific to ARM64. Obviously, there needs to be a per arch implementation, but this is definitely made to be implemented on x86 and maybe also on Power. Now, little note is that pkeys here is used for data protection, but it could be used for other things. For instance, if we have secret data, confidential data that should not be even readable for most code, we could also do that. And on ARM64, we have a use case for that actually with pointer authentication keys. Another very interesting use case is eBPF. So right now, what ensures that eBPF programs cannot, do very bad things is the verifier. The verifier has had quite a large number of CVs in the past years, meaning that, let's say that relying entirely on the verifier to isolate BPF programs is not always reasonable. And something like pkeys could help to prevent eBPF programs from writing to the rest of the kernel, for instance, or calling arbitrary kernel functions. Some interesting resources. Rick Edgecombe from Intel did something very similar in 2021 to use pks, so protection, pkeys, to protect page tables on x86. The series kind of stalled. There were concerns on performance, but as far as I understand, no benchmarking was ever performed on x86, so hard to tell how it would fare. And also, side note is that on this batching that I showed here, this piggybacks on previous work from my colleague Ryan Roberts to use to leverage the lazy MMU sections on ARM64. And I think that's it. Thank you for your attention.
I'm actually going to ask a first question. So, since I
Go
have a
ahead.
mic. So you mentioned, I remember Rick was posting this page tables. Did he use approach of batching or at that time? I just don't remember. I could check.
So I don't think that Rick used batching for the PT. So I'll come back to that slide. I don't think he used batching for the PT updates, as in I think every set PT will still do it. I'm not quite sure. I think so.
Okay.
But there's one thing he did do, and he actually commented on the list last week, is that he modified the page table allocation so that instead of essentially every time you allocate a page table page, you have to change the p key, which is not very good in terms of TLBs. He changed it so that all page table pages would be allocated from one pool, and that pool would already have a p key set for the whole pool. And so actually this last slide that I have, it's a lot of data, but just the interesting point is that if you look at the last two columns, column 3 is with batching and both pkey register switching and set memory pkey, and the last column is the overhead of only pkey register switching, not set memory pkey, and that's actually because I made a mistake. So these are original wrong numbers, in fact, but still interesting. So what we see is that the overhead of pkey register switching is really the main one, and set memory pkey, which implies TLB invalidations, is for most things not a huge overhead. Now on fork, it's definitely a big overhead, because on fork you have to duplicate all the page tables. So obviously, if you do a set memory pkey on every page table page, that's expensive. But for real life workloads, Kern bench, actually it's not that negligible, but it's okay. Let's say it's okay. But Rick's expectations that it's much less okay on x86.
Okay.
But we haven't tried, so.
Tried. Okay.
Thank you.
Other questions?
Thank you. Does ongoing rework to folios help with the performance problems, or are these not the stuff like that you want to protect?
Do you mean whether folios help with the performance of page table protection, or?
Yes, because you have a lot of them and you usually use them for the same use case, I would imagine.
I'm not sure I understand your point, because the overhead of page table protection, set memory pkey, is that we call it for every page table page, but I mean the folio is only one page in that case. Or do you mean that you have fewer page table updates? because of folios.
Yeah, instead of
Right.
because the course doesn't handle multiple page tables each differently, but
Yeah.
they are all in a folio and would use the same protection key. I
Yeah.
imagine.
Okay. But now I understand. Yeah, it's a good point. So with folios, for instance, instead of getting one page fault every 4K, you would get one page fault every 16K, meaning that you just, you also batch more, in fact, the page table updates. So yeah, I think the answer is yes. I haven't measured with and without folios, because folios, I mean, now are used quite widely on ARM64, but I expect the answer is yes. Not quite sure.
Thank you.
Other questions?
Hi, thanks. I have a question for better understanding. If I see this correctly, you could achieve the same by setting the pages classically to read only. So I understand that this is considered to be a performance improvement. Can you comment on this?
Right. So that's a good question. There's two aspects to this. One is performance for sure, because a pkey register. Well, so if I come back to the performance slide, the pkey register switch is a bit expensive. There's a barrier, but it's just a barrier. It's not like a whole TLB shutdown. So clearly much better performance-wise. But there's another aspect, which is that the pkey register is per CPU. So we make the data writable on one CPU only, and not on the whole system. So it's also better in terms of security, in fact.
Thanks.
Other questions?
Yes, thanks. So I had a question regarding the read protection that you were suggesting, right? So basically, like, so you're going to make something non-readable for like data that's confidential, for example, the struct cred. Do you also do that in the phys map, right? The physical linear mapping of the memory. Are those pages also marked as non-readable there?
So
it's like you have the whole memory mapped in the kernel, right? In the phys map, because an attacker could still read those things, right? So the data is still readable by the attacker.
I get your point. So for page tables, they're only in the linear map, so you don't have that problem. But for cred, because it's via slab, I guess you would have that problem. Yeah, that's a very good point. Right now, I guess the answer is nothing special is done. So only the slab itself is protected with pkeys. So yeah.
Yes. Okay. Thanks.
Yeah.
Other questions?
Hello, thanks for sharing. I prefer to understand how do you manage the keys? Yeah, there are the pkey keys. We are setting the pkeys.
Mm-hmm.
How to manage it? How to protect these keys?
How do you protect the keys?
Yeah.
What do you mean?
You mean the setting the pkeys? The keys is to the encryption, right?
I'm not sure I understand. So one thing important to mention is that if the attacker is able to change the key by executing the right instruction, so which is like this MSR in that case, then kpkeys is defeated. So the assumption is that the attacker does not achieve arbitrary code execution. It's only able to corrupt data, not code, for sure.
Yeah. Okay.
Yeah.
Thanks for the talk. What about corrupting function pointers and then, taking on the usual chain of prepare creds, comment creds? Actually executing these would still work, right?
Yeah, sure. But I guess the interesting thing is that you could use kpkeys to also protect structs that contain function pointers. In fact, it's quite an obvious target, most likely.
Is that a part of the next work?
Not something that we've planned right now, but definitely something that would be worth looking into. I guess the interesting thing with structs that are filled with function pointers is that if you have nothing else but function pointers, maybe you could just make them read-only, really. But maybe that's not always the case. So that's a very interesting case, I think, to look into, yeah.
All right, thanks a lot.
Any other questions? Once. Okay, let's thank a speaker.